Welcome to Part 5 of the module on an overview of pattern relationships. In previous parts of this module, we motivated the need for pattern relationships that go above and beyond traditional pattern collections. We outlined some of the common types of pattern relationships and then described some of the key concurrent and networked software patterns that are associated with the domain of avionics control systems. We've also talked about a number of other pattern relationships in some detail. We discussed pattern complements and pattern compounds, pattern sequences, and now we're about to embark on a discussion of pattern languages. We'll have two parts covering this particular topic because it's the most lengthy and involved part of pattern relationships. And along the way, we'll summarize even more Gang of Four and POSA patterns. So what's a pattern language? A pattern language is essentially a network of related patterns. And when we say network, what we really mean is that the patterns are involved with each other. They're associated. They're connected somehow. Of course, there's also the patterns themselves. Those are the vocabulary of the pattern language. Things like proxy, adapter, reactor, acceptor, connector, and so on. Patterns we've talked about before and we'll talk about again many times throughout the course. But a pattern language goes more than just providing a vocabulary and a network. It also provides an orderly process for systematically resolving design problems that occur in a particular context. In this particular context, we're going to be focusing on will be the domain of communication middleware. But be aware, of course, that you can apply patterns and pattern languages to many, many other kinds of domains, either software domains or beyond. The domain of building architects and building architecture, for example, are also places where pattern languages have been applied quite successfully for many years. This definition of pattern language may sound at first glance a lot like the pattern sequences we covered in the previous part of this module. But there's some important differences. So before we go and discuss pattern languages in more detail, let's compare and contrast patterns, pattern sequences, and pattern languages a little bit more thoroughly. In some sense, a pattern is to a pattern sequence the way a photograph is to a traditional film. In other words, a pattern sequence is a linearized presentation of related patterns. We'll take a look at such a sequence in just a minute. In contrast, a pattern sequence is to a pattern language the way that a traditional film is to some kind of hyperlinked cinema film or even a hypertext document. If you take a look, for example, at a hypertext document, you'll see that there's many different ways to traverse through that document, to learn things at your own pace or to address issues that are specific to your particular interests or needs. By the way, you might take a look at this link for more information on hyperlink cinema. There's a number of movies out there that allow you to explore the plots through various different paths through the movie, sort of like a pattern language. So let's talk now in more detail to compare and contrast pattern sequences and pattern languages. And to do this, we'll pick an example that we've been using for some time now from the context and domain of communication middleware. So remember, the patterns in a pattern sequence are arranged in a particular order that captures the evolution of a system and achieves a particular design outcome. So the example pattern sequence we'll be covering here is a pattern sequence for generating a particular broker design. Keep in mind that this pattern sequence is not comprehensive. There's many other patterns involved in developing a broker, but we're going to focus on some of the key patterns pertaining to concurrency and networking because that's the theme of the course. So what we're going to do here is we're going to walk through each of these patterns in the sequence very quickly just to give you a flavor of each one. And then we'll start talking about the way in which pattern languages allow you to traverse through these patterns in various ways depending on what kinds of requirements or needs you're trying to fulfill. The first pattern in our sequence is the layers pattern. And layers are all about structuring some complex design, like a broker, in some kind of orderly way that separates concerns so it makes it easier to plug in different implementations within different parts of the layer hierarchy. We'll be using layers in our particular pattern sequence to break up our broker into the operating system encapsulation layer, the part that deals with the so-called core broker behavior, things like connection management, event and request demultiplexing, concurrency, synchronization, fault tolerance, and so on. And then other layers that deal with actually taking the requests and getting them dispatched up to the objects themselves. Those are some of the layers you would find in a broker. You can take a look at this link to find out more about layers, or you can take a look at the POSA 1 book, which has an excellent description of the layers pattern. Another pattern we're going to use here is the wrapper facade pattern. The wrapper facade pattern makes it possible to shield the upper layer services and applications from low-level operating system portability concerns. So it makes it possible to be able to wrap the OS APIs so you can run your broker on top of different versions of Unix, different versions of Windows, different real-time operating systems, and so on. You can take a look at this paper for more on wrapper facade, or take a look at the POSA 2 book. The next pattern we'll use in our sequence is called the reactor. The reactor is a pattern that decouples the event detection, demultiplexing, and dispatching, which is all part of the inner core of the broker, from the parts that handle the dispatching to the application objects, and of course the application behavior itself. This pattern appears in the POSA 2 book, and you can also read an earlier draft online at this URL. The acceptor connector pattern is a pattern that allows you to separate connection establishment and service handler initialization from the actual work that the service handlers do once they're connected and initialized. This is another POSA 2 pattern. You can read about it at this URL. The half-sync, half-async pattern makes it possible to be able to decouple your design into a lower layer part that doesn't block and only has one thread of control, and then an upper layer part which can block and has multiple threads of control. This is a POSA 2 pattern. You can read about it here. And it's important to realize that half-sync, half-async also relies heavily on a pattern called monitor object. Monitor object ensures that there's only one method running inside an object at a time, and makes it possible to serialize and schedule the interaction of methods on that object from different threads of control. And it's commonly used to provide a synchronized queue in a half-sync, half-async pattern-oriented architecture. Monitor object is also a POSA 2 pattern. It's widely used in Java. You can read about it here at this link. When we start building other parts of the broker, it turns out we may want to make them more flexible, much as we talked about in the previous part for pattern sequences. We may want to have different implementations of the broker mechanisms by using the strategy pattern, which is a gang of 4 pattern. We might want to be able to combine strategies together in various ways to make them semantically consistent when they're composed using the abstract factory pattern, which is also a gang of 4 pattern. And we may want to be able to dynamically configure the strategies in abstract factories in such a way that we don't end up incurring the overhead in time or space or power for strategies and factories that we're not using at any given point in time. And that would be the component configurator pattern, which is a POSA 2 pattern, also described here at this link. All of these patterns together help to form one way to design the broker pattern, which is a POSA 1 pattern that you can read about at this link. So the key point here is that a pattern sequence allows us to walk through a set of design considerations, and it provides us with an orderly way to resolve those design problems. The downside, of course, with a pattern sequence is what we end up with when all is said and done is a point design solution. We've provided a broker that works in a particular way. But that's not always the most important thing to do if you're trying to build software, especially reusable infrastructure software like a broker. So to see how we can get around that particular problem of point design solutions, let's talk about pattern languages. So a pattern language provides a set of patterns that build on each other to help document the successive progression of design decisions, transformations, and most importantly, for the context of this discussion, alternative paths through the design space. This is one of the key areas where a pattern language goes beyond a mere pattern sequence. As you can see from this diagram, this illustrates the patterns we've just talked about arranged as a pattern language with different paths and alternatives that you can traverse depending on what it is you're trying to do. Keep in mind, of course, once again, this pattern language for Broker is also not comprehensive. You can take a look at POSA 4 and POSA 5 books for more information on other aspects of a more comprehensive pattern language for distributed computing. Here's one path through the pattern language. This path goes through layers, wrapper facade, reactor, and acceptor connector. And it provides a very simple Broker solution where there's only one thread of control, and it doesn't provide any way to be able to parameterize or modify or extend various strategies used to implement other parts of the Broker. So you would use this particular path through our pattern language if you're trying to write a very simple Broker application. This next slide illustrates a more involved path through our pattern language. We're still going to keep the same core set of patterns, layers, wrapper facade, reactor, and acceptor connector. But now we're going to also support some degree of flexibility by allowing the use of strategy, abstract factory, and component configurator to be able to reconfigure various mechanisms in the Broker to tune them more appropriately for particular needs of particular applications. Here's yet another way to traverse our pattern language. This particular path through the pattern language is going to focus on scalability and flexibility. Here we keep layers, wrapper facade, reactor, and acceptor connector, as well as the other patterns for providing different mechanisms through strategy, abstract factory, and component configurator. But we add in two new patterns, half sync, half async, to allow us to have a pool of threads, and monitor object to allow us to be able to have a synchronized request queue between those threads. And the final path we're going to show through our pattern language is one that emphasizes predictability and flexibility. The main thing that happens here is we keep all the other patterns as before, but instead of using reactor, half sync, and monitor object, instead we add in the leader followers pattern. And as we'll see in the next part of this module, leader followers makes it possible to have a thread pool that incurs less overhead than half sync, half async. And as a result, it makes it more efficient and more predictable, although half sync, half async is more scalable. So it's a question of which type of trade-off you're trying to emphasize in your design. There's a number of steps that are applied when developing and using a pattern language. Here are what those steps do. One of the key steps that you need to do is identify what the key problems are that need to be resolved and what order to resolve them in. For example, here's just a little snippet of some of the problems that we're addressing in our particular pattern language. We're trying to find a way to enhance the scalability of the Broker by processing requests concurrently. We're trying to figure out how to efficiently synchronize request queues between different layers of threads. We're trying to find ways to be able to swap in and out or plug in and out different Broker mechanisms and so on. These are some of the problems that we're trying to identify. And depending on what the problems are, we may have to do them in a particular order. For example, you're most likely going to want to figure out how to have a concurrency architecture before you start worrying about what kind of synchronized request queue you need, if you need one at all. We also have to figure out how mutual dependencies between these problems must be resolved. For example, if we're going to have a half sync, half async approach, then we're going to need to be able to have some type of synchronized request queue. Well, if we start fiddling around with some of our Broker mechanisms, it's possible for us to make some selections for synchronization primitives and so on that might be at odds with some of the mechanism choices we selected to resolve earlier problems. So we've got to make sure when we apply the various patterns in a particular order that they're consistent with each other and resolve these mutual dependencies, because things aren't entirely isolated, and choices in one part of the solution space or problem space will affect the other choices available in other parts of the solution and problem space. We also have to keep in mind how to resolve these individual problems given the context in which they're being applied. For example, if you're developing a broker for some kind of electronic medical imaging system, then scalability and performance and throughput are probably key important parameters. So you might tend to use a half-sync, half-async approach. In contrast, if you're going for something like an avionics control system, then low latency and predictability would be important. And that might suggest a different solution, perhaps something that's using the leader-followers approach. And that leads to the other major point you have to consider when developing and applying patterns. Knowing what the alternatives are for each of the problems, and then figuring out which ones you want to apply. Should we apply a reactive approach and make things simple? Should we apply a half-sync, half-async approach, make things scalable? Should we apply a leader-followers approach, make things more predictable? That's an open question, and each architect, each team, each developer ultimately has to understand these trade-offs at some level in order to be able to apply and navigate through the pattern language most effectively. We'll come back and talk more about these particular alternatives in the next part of this module. But to summarize this part, a pattern language integrates groups of related patterns to enable larger scale reuse of software architecture and design. We're not just using individual patterns in isolation as pattern islands. We're not just using a handful of patterns in pattern complements or pattern compounds. We're not even using just a sequence of patterns that lead to a point design solution. Instead, we have a pattern language that allows us to navigate through the design space and select the alternatives that make the most sense given what our key design requirements are.